The binomial theorem is a good example of the combinatorics, the combinations in particular that we've been doing. So we're going to approach this from a combinatorial perspective rather than purely algebraic. Just doing a couple of examples. First of all, with the square of a binomial, you know how to multiply or square a binomial and get the result a squared plus 2ab plus b squared. We can think of it as a plus b times a plus b, and in doing it that way, use distributivity, or what a lot of people like to call FOIL, not my favorite acronym, but we'll get all four of those terms in so doing that. And notice that these terms, the first one here comes from taking the a's from both of those. The second one comes from taking the a from the first one and the b from the second one. The third one, maybe I can get a third color here if I'm clever about it, comes from taking the b from the first one and the a from the second one. And the last one, let's see, let's just go to black and take b and b. That means taking the b from both the first and the last ones there. So each term here, each has one term from each factor of a plus b. So each of these took one of the terms to form that product down here. If you cube it, then it's the square times the first power of a plus b. So above we have the square, and then if you take that times a plus b, then the first one would be aa times a, so that's aaa, and then I will take ab times a, and that's aba, aba. Then we have baa, baa, b, then it'd be bba, bba, and now we'll multiply them all by b. AAB, ABB, BAB, BBB. So we get 8 terms there, and we'll combine them in the normal way. And in fact, if we look at it, then we get a squared b comes from this term here, and this term here. And basically, what's going on here is this term in the AAA that we have there comes from taking an a out of each of these. And then the second one, ABA, comes from taking an a here, a b from the second one, and an a from the third one. Yeah? And in like fashion, you can see that each of these terms comes from taking exactly one of each of the factors of a plus b above. So, for example, let's just take another one here. Let's take the BAB. So BAB has the b from here, the a from the second one, and the b from the last one. So each term is exactly the same thing. Each has one term from each factor of a plus b. Now, how many of these then gave us the 3a squared b? Well, the number that gave us the 3a squared b, 3a squared b has 2 a's, 1 b. So in how many ways can we get 2 a's and 1 b by choosing one from each of those? Well, we choose 2 factors of a plus b for a's, and the other one that gives a b's, and so there are 3 choose 2 ways to do that. And that's why we have the 3 there. That's why we got 3 terms of that sort that have 2 a's right there and 1 b. Yeah, that works generally. You can show that that continues by just proceeding with that argument and seeing that it works each step as you go from one to the next. It's an inductive argument. going one step to the next works in the same fashion, and so we can say that it works in general. And so in fact, when we're taking the a positive integer n and looking at a plus b to the n, then what we'll do is we'll have an a to the n that chooses a from each factor. So we're choosing 0 b's, and let's use that and then choose b from none of them, b from 0 of them. And the number of ways we can do that is cn0, and then we'll have n a's. The next one we'll choose b from one of them. Well, there's cn1 ways. Choose b from 1. Or choose 1 to give us a b. Maybe be a little more clear. Choose one factor, 1 of a plus b factor for the b, and the rest give us a. So we'll get 1b, and the rest give us a, and minus 1 give us a, and so this pattern continues all the way down to cnn, b to the n, where we choose b from all of them, b from all. So we choose n of the factors to give us a b. Yeah, so that's the binomial theorem, and that's basically the proof of the binomial theorem. The alternative form uses summation notation and the binomial coefficient, so let me go over this real quickly here. The summation notation, which is real convenient. If you haven't seen it, what we'll do is we'll write a big sigma for sum. The Greek letter for s is sigma. And in this case here, I'm letting k start at I. K will go all the way up to j, taking one incremented by 1 each time. And we're summing whatever ak is. Well, k is first I, so that would be ai. K will next be one more, so it'll be I plus 1. That's what k would be. K here, that's an arrow, etc., until we reach k is equal to j, and so that would be the last one there. So that's what that summation notation means. And I'm going to do a couple of examples real quick just to show you. So the sum, k goes from 2 up to 5, of 3 to the k would start with 3 squared. K is 2. 3 cubed would be next, 3 to the 4th. And we go all the way up to where k is 5, 3 to the 5th. We'll call k the running index, or the index. The sum as k goes from minus 1 to 3 of k squared. Now here k is in the base here. So k will start at minus 1, and that'd be minus 1 squared. Then k goes to 0, so that'd be 0 squared. K goes to 2. 0 after that is 1. So it's 1 squared. Then k goes to 2, 2 squared, all the way up to 3 squared. So that'd be that sum right there, which, we could easily count that. What is that? That's 1 plus 1 is 2, plus 4 is 6, plus 9 is 15. So that's maybe not so important. But the point is that with this kind of notation, we can collapse the sum in the binomial theorem. Also, the cnk is called the binomial coefficient. Why? Because it appears in the binomial theorem. And instead of the cnk, the notation n, choose k is used with the parentheses looking like a fraction enclosed in parentheses. There's no fraction bar, however. And so in that form, I'll scroll down so you can see it up here. The result we had above, a plus b to the n, a plus b to the n, is equal to the summation. K starts at 0. That'll be the k right there. Let me change color on that. So there's the k appearing. Here k is there, and k is the first power. K is there, k is there. K starts at 0, and it's n choose k, a to the n minus k, b to the k. Okay, so that's the binomial theorem, which tells us how to take powers of binomials. Okay, this clip now is over.